Hello everyone, today in this video we are going to talk about the torque on a current carrying loop, and after this video you should be able to derive the expression of the torque. So out here I am considering two poles of a magnet, so in between there is a uniform magnetic field. So I am keeping a current carrying loop which is taking the current in clockwise direction. In this conductor the current is going upward and magnetic field is going towards the right. So I can use Fleming's left hand rule, and using the Fleming left hand rule the direction of force is into the plane of screen. So this force will try to take this side of a conductor into the plane of the screen. Similarly, if I use Fleming's left hand rule out here, so current is going downward, magnetic field is going towards the right, so the direction of force will be out of the plane of the screen. So these two forces, as you can see, they are opposite in direction, and but line of action is not same. So this two force will form a couple and it will rotate the coil this way. So if you keep a current carrying coil in a uniform magnetic field, it rotates due to the torque produced by the forces. So there will be no rotation in y direction because the forces on this part of conductor and this part of conductor will be equal and opposite, so there will be no force. So now let's consider this diagram to derive the expression of torque. So I am considering a coil PQRS, and the sides of coil is B and A, and it is rotating from this axis, and n dash vector is a vector which is perpendicular to the plane of the loop, so I can call it area vector of the loop, and B is magnetic field, and angle between n dash and B is theta. And this is the diagram. If you look from the top, so you are looking from the top, Q and R is out here, so forces are, one is going towards upward direction, one is downward direction, and this is the length A of the coil, and I can resolve this A into two component, A cos theta which is towards the angle, and E sin theta. So the perpendicular distance between two forces is A sin theta. These are the assumptions. So I am considering the loop PQRS. B is magnetic field, I is the current flowing through the loop, A is the breadth of the coil, B is the length of the coil, and n dash vector is the normal vector to the plane of the loop, or we can call it area vector of the loop, and theta is angle between n dash and B, and n is the number of turn, and this n dash and n are different, and n is the number of turns. So we are not considering only one turn, we are considering many turns. So according to Fleming's rule, the force on this conductor and this conductor will be equal and opposite, so they cancel each other. It will be vertically upward and vertically downward, so they will cancel each other, so there will be no force in y direction. So now the force on PQ, wire PQ is, we already know force on a current carrying conductor in a magnetic field is BIL sin theta. So B is magnetic field, I is current, and L is the length, so length out here is B. And similarly the force on this side of the conductor is IBB, and sin theta is 90 degree, the angle between magnetic field and current is 90 degree, so I am not writing sin theta out here. So these two forces we have already discussed, they form the couple and try to rotate the coil, and the torque on the coil will be either force into perpendicular distance, and perpendicular distance between these two forces A sin theta. So force is IBB and perpendicular distance is A sin theta. So torque is equal to AB sin theta. So this AB is length into breadth of this coil, so I can write this to be area. So this is IBA sine theta. So now if the coil has n turns, then I have to multiply this with n. So now I can take this NIA as small m, and which is magnetic moment of the loop. So torque is equal to mb sine theta. Now in vector form, so when we see sine theta, we make the cross product. So this is m cross b. So m is a vector. Now let's see the special cases. So this is the expression for the torque. This is tau is equal to mb sine theta, and this theta is the angle between area vector of the loop and the magnetic field. First case, the area vector and the magnetic field are parallel. So this is the loop I am looking from the top, so this area vector will go with magnetic field. So theta is equal to 0, so tau will be 0. So torque is minimum when the loop is perpendicular to the magnetic field. So don't get confused, I am saying angle is equal to 0, but when the angle between the magnetic field and the area vector is 0, that time our loop will be perpendicular to the magnetic field. So that's why I am using the term perpendicular when angle is 0. That time torque will be minimum. So now this time the angle between magnetic field and the area vector is 90 degree. So this time I can use theta is equal to 90 degree and tau will be mb. So the torque is maximum when the loop is parallel to the magnetic field. Loop is parallel but area vector is perpendicular. So don't get confused with this 90 degree and parallel. This is the end of the video. Thank you. Don't forget to like and subscribe.